Okay, hello everyone, and welcome to this short lecture on delay-based effects, delay-based audio effects. So I'm going to spend a few minutes introducing the basic concept of delay. It's really one of the simplest possible audio effects, at least in its basic form, but very advanced things can be done with it. And after introducing it, talk a bit about how it's used, why it's used, and then how to set it up as a simple effect to use in Juice and C++, and hence developing an audio effect plugin uh, based on delay. So here we go. So the basic delay, as I mentioned, is really quite simple. Let me just fix a little typo on the slide here. Okay, don't know why that occurred. The basic delay is simply that the output is equal to, in this case, a sum of the direct signal, that's x of n, plus some gain times a delayed version of that original signal. The gain is almost always going to be set to a value less than 1. If it's at a value greater than 1, one can experience feedback where the output grows over time. So you can imagine a gain of 2 here in this equation. And if the input is always 0 except for one pulse, one sample that is at 1, then the first output is going to be 0 plus 1, the first non-zero output. And then the next output will be, after a while, after more zeros, it will then have 1 times 2 for the gain 2 plus current input of 0, and so an output of 2. And then after a while, an output of 2 times that, 4, 8, 16, and so on. So that grows exponentially over time. And how that is dealt with is simply ensuring that when gain is implemented in this form of delay, it's never set to a value greater than 1. Now, if we look at this delay, what does it mean for audio? So in practice, the delay value that is chosen, that says capital N in the difference equation, could be a value here, it's just a sample number, but in time, it could be a value from milliseconds or even less than milliseconds, sub-milliseconds, to a value of several seconds. If one is dealing with samples for a sampling rate of 44,100 samples per second, which is the typical value with compact disc and a lot of audio formats, then that suggests that in 1 millisecond there's just over 44 samples, or essentially that the period between samples is about 23, bit less than 23 microseconds. So it's a very short time between samples, very quick. We don't perceive the difference generally from one sample to the next. So bear with me while I just check that the setup is all set. And yeah, should still be good. Um, So delay is the building block of many different effects. The idea is that it takes the audio, the incoming signal, and plays it back after a certain delay time. Delay can be used to bring life to dull mixes, to fill them out, widen an individual instrument's sound, provide more sustain, and also to allow a musician to solo over him or herself. By having a very long delay, you can play back what you were playing previously and solo on top of it. Delay is also the building block for many other effects that simply by having more delays combined together or varying the delay or adding in some filters, you can get things like echo, reverb, chorus, and flanging, and many more. So we introduced the basic delay just a couple of slides ago, but many times when delay is implemented, it is with feedback. And the feedback is sometimes referred to as regeneration. So look at this figure in the top right here. There is a gain G so that the signal X of n goes through a delay, and then one path it takes is multiplying it by the gain and putting that back into the original input. It's a bit different from the situation that we dealt with above, where there's a gain only on a feed forward path. Here we have a gain being fed back. And so for this sort of system, the output is at first x of n, and then at another time x of n plus some delayed and attenuated based on g form of the original signal. So imagine an impulse like a clap. Then what one hears is that impulse plus a delayed version multiplied by the gain plus a delayed version multiplied by the gain again, and so on. So the single clap becomes, and as long as G, the gain, is set to a value less than 1, then for a single impulse, it will decay towards 0 over time, which means that for a rich input signal, you still don't have unbounded or unstable behavior. But if the gain is bigger than 1, you can get feedback growing over time. It's what's known as a howling effect. In live environments, you often hear that when a singer first steps up to the microphone. The gain on the singer's microphone might be so high so that they are heard over the other instruments on stage, but a very high gain means that the sound of the vocals coming through the amplifiers or the speakers around the stage might be loud enough such that that then gets fed back into the input into the sound system from the singer's mic and possibly elsewhere. And if that gain in the feedback loop is large enough, then you get just the same sort of unstable and unbounded feedback as you can have when the gain is greater than 1 here. So we would like to be able to derive the output in terms of input. And this is also beneficial because then with a bit of math, one can see what happens in the frequency domain. So for given input frequencies, what happens to the output frequencies, and one can usually determine whether or not a system is going to have bounded or unbounded behavior based on the block diagram. In this system, it's fairly simple. It just depends on whether the gain is less than or greater than 1. But you can imagine more complicated filters in the feedback loop and additional gains and so on. And so it becomes something that is possible to derive analytically, and that's useful to know beforehand whether the design is unbounded or not. So here we have the two equations. So if we look at the second one, you can just say that y of n, the output, is the sum of x of n going into it and this delayed version also going into it. So that's the sum of x of n plus, let's call it d, a lowercase d, plus d of n, which is that input right before the summation. So that's what we do, what we have for y of n. And then what is this delayed value that goes in? Well, it's a delayed version of x of n plus the previous output multiplied by g. So that's this equation. D of n equals x of n minus capital N for the delay capital N plus g times d of n minus capital N. That's what gets fed back. and output into y of n, which then gets summed with x of n for the final output. So we have these two equations. I'm going to, let's see. No, this should be good as is. Yeah. So looking at this again, let's delay that first equation. So rather than d of n, sample n, it's d of n minus capital N. So what is the delayed version? Equals these two terms. Let's see. D of n. Yeah. What we did here is we take this equation, y of n equals x of n plus d of n. So I'm going to change this slightly because I noticed another mistake. Okay, so what we do is we take y of n equals x of n plus d of n. That's the input to this final output, y of n. And we delay all the terms here, and then subtract both sides by the delayed version of x of n. So we get that the input into this summation for y of n, once delayed, equals y of n minus capital N minus x of n minus capital N. So then after, whoops, that was too quick. So then we have the d of n here, and we put that d of n directly into this d of n. So we simply replace the delayed input into that gets summed with the original. We replace that with our known form for it right here. So we get y of n equals x of n plus, instead of d of n, x of n minus capital N plus g times d of n minus capital N. Now we have these two equations. We can replace the d of n minus capital N in both of those equations. That's what we get in the second to last equation. And then we simplify that to get output, y of n, as a function of input x of n plus previous input plus previous output. So all we do is we have this dummy variable d of n here. We figure out what that is in terms of x of n and y of n, or delayed versions, and we plug that in so that we get output just as a function of previous outputs, previous inputs, and inputs. Now, this is a useful thing for you to know if you are dealing with a specific circuit and want to analyze all of its properties, or just what the behavior in the frequency domain, stability, things like that. What does delay do on an instrument? So we're going to play a few sound samples over this in the next few slides. Here we have an example of playing delay with a short echo, relatively short in time, but one that you can still determine that it's an echo rather than just a frequency modification. So say up to 100 milliseconds, and it creates a sort of doubling effect. Let's listen to this. We'll play first a simple guitar riff, and then the same thing, but with doubling the sound using a short echo. So hopefully you heard a small difference between those two, a sort of richer, more filled out version in the second one. When longer delays are used, and so that there's almost a gap, or can be a gap, between the original sound and the delayed version of that sound, then it's no longer a subtle effect. One can use delay to do things like match the tempo of a song. So if you expect to hear notes every quarter second, then set a delay of a quarter second, and you may only need to play half as many notes, for instance. Um, so this is actually a technique used by some guitarists, some other musicians, most notably The Edge from U2 made very heavy use of guitar and a lot of the heavy use of delay in a lot of the U2 albums, to the point where there's actually people online who try to deconstruct all of his delays. And he was actually quite a minimal guitar player, often, even when the recording ended up hearing a lot. It wasn't laziness on his part, it was his particular technique. So in the sample I just played, a long delay is used of about 1.5 seconds so that one starts to hear the copies of the original notes a long while after, and yeah, allows one to play less and get more sound. When very long delays are used, it's essentially a sampler. So sample what you were playing before, play back over yourself, use those samples in whatever comes next in the music. For a long time, these sampling units were quite limited because of memory and storage issues, so they'd only have 2 seconds or less. Now I don't think there's really any significant issues in storage, so they can store things played minutes back or further. Um, Delay is quite important in the mix because it can be used to make the mix sound bigger, make it sound less sparse, that there's more going on. It can also be used to fill out individual instruments' sound so that when mixed together, they they fit more nicely in the mix. So you can imagine a situation with violin and a snare drum, for instance. So the snare drum is quite short, quite impulsive, and different frequency range. But by having delays, you're filling out the sound, you're making the transient sound as if they're a bit longer, which makes them fit with the very slow transient violin. So here's an example of something else, which is the use of delay for spatialization. If one has a delay between left and right channels, then a short delay, um, say on the left channel, might make it appear as if the right was heard first, and hence as if you are closer to the right, and so that the source comes from the right. Now, this example probably will not work well within the YouTube video, so I encourage you to go to GitHub, download the samples associated with this lecture, and listen to it properly. But what you're getting here is probably the sound directly from my loudspeaker setup, and OBS, what I'm using to record, may not be picking up the spatialization well. Let's see. Then we have slapback. Slapback is not a new algorithm. It's simply choosing a delay that is not super short, where you're mainly modifying frequency content, and not so long that it appears like distinct echoes. So it's more an immediate copy of a sound, one where you might be talking near a wall that's quite a short distance from you. So you get the slap back type effect. Here's two figures related, or one figure, one table, but related to the types of delays and the amounts of delays used for different effects. First thing to notice is they don't agree with each other. So people use different definitions, and there isn't formal requirements that the delay must be this much when used in chorus and so on. But the general trend of both of the figures are the same. The other point is that these don't really do justice, at least the one on top, to the fact that delay can extend over such an extreme range, from sub 1 millisecond to hundreds of milliseconds. And that's why, to some extent, the lower figure has a logarithmic axis for the amount of delay. Multi-tap delay is what's used for chorus and quite a few other effects, and it simply involves having more than one delay. So ideally, with multi-tap delay, it's an FIR filter normally, where there is a delay and then optionally a gain, taking that delay to the output, or it passes through another delay where there could be another gain and attenuation, taking that version to the output, or it passes through another delay, and so on. And then all the versions pass to the output, summed together to produce the final output. So let's have a listen to 4-tap delay in action. Multi-tap delay is a fairly simple extension of basic delay, but one can also make it much more complicated by allowing feedback from each delay output to the beginning, or even just to a previous stage, not so far as the beginning, or other filtering in the loop. It's quite easy to create an unstable system this way, so one needs to be careful in design. If you look at only a single tap, then the sound repeats according to the total delay time to get to that point. And the input appears at the output before that total delay time. So, let's listen again, sound produced with 4-tap delay, and then we're going to vary the amount of additional delay for the 4th tap. First move it lower, then move it higher. So you should have been able to hear some differences there. Then we have what's known as comb filtering, and I'll probably discuss this in a lot more depth in later lectures. But the idea is, supposing you're recording a musical instrument with 2 microphones, and there are many reasons to do this. It might help you get the timbre you want, a sort of inside microphone and an external microphone. Combined together might allow the sound engineer to control the timbral characteristics of that musical source. But the problem is, imagine a particular sinusoid going or emanating from that musical instrument, and so being picked up by the 2 microphones. One of those 2 microphones might, at a particular time, have the sine wave at its peak. The other microphone, which is a different distance away from the source, might at that same time pick up the microphone at its trough, at its lowest, pick up the sinusoidal output from the musical instrument at its trough, at its lowest point. And so what happens when the peak value and the trough value are added together? They cancel out. You might have something like a +1 and a -1 in terms of audio samples. And so for particular frequencies, one has a sharp attenuation in the frequency response there. And this is known as comb filtering. And the solution to deal with comb filtering is simply to adjust the distance between the microphones. So bear with me 1 second. Okay, so for implementation of digital delay, essentially we just need to store previous samples. And then if it's a previous sample that we need, say one that was 10 milliseconds ago, then by storing at least the last 10 milliseconds, you can always go back and take that previous sample and either output it or sum it with the other samples or use it in a feedback loop. This is somewhat challenging to implement. First, we're in for the VST standard and for most other forms of audio processing, one often deals with a block of audio at a time. So the low-level processing, an algorithm, a bit of code, a method might get, say, the last 64 samples. Well, what if the delay is more than 64 samples? Or what if you want to get the sample, just 2 samples ago, but it's not within your block, it's within the previous block. So this suggests that one always needs their own buffer, that can be whatever length you want, and that buffer needs to always keep the last however many samples, 64 in the case I just gave. So it always needs to remove one sample, add one more, or alternatively it could create a whole new buffer for each sample, but that would be a very difficult way to work. If it simply removes the oldest sample, adds the newest sample, then what does that mean if you want to always be reading the newest sample or writing the newest sample in the right location? You need pointers to keep track of where you want to read and where you want to write, and those pointers always move while you're adding and removing samples. So we're going to look at this and we're going to do a basic implementation of this. Here we have 12 samples linearly in an array, and we are always looking at, say, x1 to x11, so 10 samples later. We have the read pointer at x of 1, the write pointer at x of 11. Then we need to increment one sample forward. So we gain a new sample into the array. We take the oldest sample in the array, x of 0, and we write over it the new sample, x of 12. Our write pointer was at x of 11. We increment that forward, and so it wraps around, it's at the end of the array, wraps around to x of 12. Our read pointer was at x of 1. We're reading a very old sample, and so we need to increment that one forward as well, x of 2. So here, what is the distance between the read pointer and the write pointer? It's not 2 samples, it's actually from x of 2 all the way to the end and wrapping around to x of 12. So it's 10 samples. Next sampling period, increment both the read and write pointer. You don't need to make use of wrapping around here because neither one is at the end of the array. So this is basically a direct implementation of delay as it appeared in the very first slide. Um, you are always wrapping around, and so if you want the sample 10 samples ago, you just read that old sample. Okay, let's see. We're going to implement delay with a simple VST plugin. So we can use our hello world with a user interface from the first week, from getting started, the most basic introduction to C++ VST programming would use. We, in the GitHub code for that, we have a generic user interface version, and that's the simple version to use. So we need to do the same steps that are done over and over in our plugin development. We define variables in the plugin processor header file. We set them up in Prepare to Play, and we edit the process block. Here, we need to keep read and write pointers on a circular buffer and make sure that incrementing the pointer on one channel does not affect the other channel. Because typically we have left and right channels. And so if you say move the pointer one sampling period forward and now look at the other channel, we're pointing to the wrong place. So one might keep two pointers, or one might only update them after all of the channels have been dealt with. So let's start first with the plugin processor header file. This is where one has to think beforehand, sort of sketches things on the back of an envelope or a napkin and says, what am I going to put on my user interface? What are the parameters that I'm going to need to always be modifying and keeping track of? So first, the parameters on the interface are the controls primarily for the plugin. In this case, our delay time, a feedback parameter, because we're simply going to implement basic delay with feedback, and how much of a dry-wet mix. So how much do we have the original signal versus the delayed version of the signal? We also define the buffer. Juice has a built-in method to create a buffer of audio samples. So a little easier than specifying all of the characteristics. For audio samples, we just use the audio sample buffer. And then, for keeping track of things in our circular buffer, we need to know the buffer length and the read and write position. Now, if we look back, we start, since we've defined the variables, we now set them up on the user interface before further work in other methods. So we add the parameters for the delay time. We are saying add this to the user interface, a parameter for delay time, which ranges from 0 to 2. So here it's in terms of seconds, and has the default floating point value of 0. We add feedback from 0 to 0.999. We don't let it go to 1 or above because that would be unbounded. And it defaults to 0. So in the initial situation, there is no feedback whatsoever. And then we add the dry-wet mix, which can go from 0 to 1. Initially, it's completely dry, so it only uses the non-delayed version. And because the delay time defaults to 0 as well, again, we aren't delaying. We aren't delaying, and there's no feedback in the default values. Okay, so now, just to clarify what had been said, we have in the header file defining the parameters that are on the interface, and then defining the parameters that we'll need to keep track of for the circular buffers. Now we can move on to prepare to play. We get the delay time, and at this point it's using our default delay time because there's been no interaction with the user. We set a length for the delay buffer based on the sample rate. So we're going to set that up to 2 seconds. 2 times however many samples is in 1 second. We set the size for that also with 2 channels, so a left and a right channel for the delay buffer length. And we set the read position as a function of the write position. Basically, we're keeping however many samples of delay for the distance from read to write pointer with some wraparound. That's this modulo operator here. So we have allocating the, let's see. Okay, yeah, we first allocate the delay buffer, and then we determine the delay position between read and write pointers. Now we can finally move on to the process block. In the process block, we define variables. Everything in the beginning up to and including sample rate are fairly standard, just getting information about what's going on in the process block. Then we get the values from the user interface. We could make these global values, but in this case, we just get them every time the process block is called. And then we once again get the read position as a function of write position. In our case, they are always the same distance apart, but we could have effects where the delay time is being varied over time. And for the second half, that's where we apply delay. So for all of the samples in the buffer and all of the channels for each sample, we specify the input as the write pointer for the buffer, and we have the delay data from the write pointer for the delay buffer as well. The delay data, so our written delay buffer, the delay data at the write position equals the input plus the delay data at the read position times feedback. So basically, let me see, I'm going to try to jump back here so you can see. Okay, yeah, so the format might be slightly different, but essentially we have, bear with me so I can describe this well. Yeah, we have what is being output here is the input x of n plus delayed value times the feedback. And so that goes to the output. And then let me now jump all the way back again. And finally, we use the dry-wet mix where we have our original input signal, and if it's fully dry, then the dry-wet mix is set to 0, and so it's only the input signal. If it's fully wet, then the dry-wet mix is set to 1, and so none of the input signal, only the delayed data at the read position. And finally, this output goes to the output buffer in terms of what we play. Then, after we've done this for every channel, we increment the read position and increment the write position, where if they go to the end of the array, we wrap them around to the beginning of the array, read position 0 or write position 0. So that's what I just described. Let's see how this looks. So here's the delay plugin. You can just look at this in GitHub if you like. We don't do anything with the plugin editor because we're using the generic user interface. But if you look in the plugin processor header file, we define those parameters as mentioned previously. And then if we look in the plugin processor CPP, here's where we set up the interface. Right in the beginning of the plugin, the constructor, and in prepare to play, we allocated the buffer itself. And finally, we have the lines of code with comments for doing delay with feedback. And that's what was shown on the previous slides. So I'm going to try to show you how this looks in action. So I might need a second while I set this up. Okay, you should hear noise. So I'm going to, let's see. I'm going to show you what's going on here. We have the delay plugin, which is what is built straight from this code. So the interface looks as shown. And we have another plugin which we call Tester, which is available on the GitHub site associated with this lecture and with all of the lectures here. I'm going to see if I can bring the tester over so that you can see it. And it just generates some default signals. So it could be a noise signal, a pure sine wave, a pulse wave, like a tick, tick, tick. Or it could play a file, play an audio file that we have recorded somewhere. So we're going to use the pulse wave. Let's see. Now this is a good one, I'll turn it down for a second. This is a good one for testing delay because you input a pulse, you hear, is there a delayed version, is there feedback? So let's try this out. Okay, that's good. Let's see if we can have just a single delay. That's good. We can increase the delay time. The delay time is so much that it's actually occurring very close to the next sample, so it seems short. So let's try it like this. that shows a nice little delay. And now what happens if I'm going to lower the frequency. Yeah, so it's a very long wait. We'll increase that a little bit. Okay, so now I'm going to add in some feedback. And maybe a shorter delay. And you hear that feedback, attenuated versions. And that's it. That is delay in operation. Please check out the other videos and use the code in the code repository on GitHub to play around with this further. And thank you all.